Now, we want to draw the connection between inverse functions and composition. So here I have a statement. Two one-to-one functions, f of x and g of x, are inverses of each other if and only if you can show two things, okay? So two functions, two given functions, are inverses of each other if you can show two things. Number one, you'd have to show that f composed with g at x gives you simply x. And the second thing you'd have to show is g composed with f at x is simply x. If you can show these two things, then the two given functions f and g are indeed inverses of each other. So we'll now look at a couple examples going through or illustrating this fact. All right, everybody, example 1 from 4.2, inverse functions. So show that the two given functions are inverses. All right, so let me show you which two functions we're going to be dealing with, all right? So the first function that I have for you, and this is given, is f of x is equal to 5x minus 2. That's the first function, okay? And then the next function I have for us is g of x is equal to 1/5 x plus 2. All right? So the challenge, the job that we have before us is, are f and g inverses, yes or no? Now, if they are inverses, then these two things must be true. F composed with g at x must be x, and the other way around as well, g composed with f at x must be x. So you have to confirm both of these things if the answer is yes, that these two functions are inverses, all right? So let's go with condition number 1. Let's try to show that f composed with g at x is equal to x, okay? Now, keep in mind, both of these things must be satisfied. Both of these statements must be satisfied in order for f and g to be indeed inverses. All right, let's go for it. Let me move this page up a little bit. All right, cool. I have a little bit of space here on my board. So the first thing we want to, I'll even label it number 1. We want to inspect what f composed with g at x is equal to. Let's check it out. All right, so let's see what this is equal to. All right, by definition, we all know by now that f composed with g at x means f of g of x, right? We talked about that in an earlier lesson. All right, so let's see. Let me move this board up a little bit. All right, so this then is equal to, come right here, f, all right, of, now g of x is 1/5 x plus 2. All right, so then we have to plug this expression, 1/5 x plus 2. This expression, we need to plug it into function f, which is up here. So this input variable right here, x, that variable must be replaced or substituted for this expression here. All right, so the way that looks is 5 times 1/5 x plus 2 and then minus 2. All right, let's see what this turns out to be. We're going to have to distribute this 5 times this and 5 times that. All right, so let's see. 5 times 1/5 is just 1, so this is just 1x. 5 times 2 is 10. And don't forget about the minus 2, all right? So then this turns out to be equal to x plus 8, which is not x like we said in the beginning it had to be. Let me remind you, let me bring this board down a little bit. Right there, okay, right here. In order for f and g to be inverses, f composed with g at x must simplify to just x, but it did not simplify to just x. f composed with g at x simplified to x plus 8, which is not equal to x. So then what we can conclude right now, there's not even a reason for us to check condition number 2. We're done because it failed right away. What we can say is f and g, all right? Let's say f and g are not inverses. Okay? They're not inverses of each other. Okay, let's look at another example. All right, guys, we have a brand new example here, and we want to show that the two given functions are inverses. This time around, excuse me, you have function g, which is defined to be 2x over x plus 1. This is a rational function, all right? The other function I have for us to consider is h of x, which is defined to be x over 2 minus x. All right, the question before us is, are these two functions inverses of each other? All right. Now, in order for these two functions to be inverses of each other, two things must check out to be true. Okay, and I'll remind you what must be true. Two things. Number one, g composed with h at x must be x. Okay? The second thing that must be true in order for these to be inverses is h composed with g. That looks like hog, but it's h composed with g at x must also be x. So we need to possibly go through both of these, and confirm that we're just getting x, all right? And if we can show both of these to be true, both of these statements, then we can conclude at that point that g and h are inverses of each other, all right? So let's see if we can do it. Let's go for it. All right, so I'm going to need some room here, all right? So the first thing I want to show is g composed with h at x, all right? So let's go for it now, all right? So g composed with h at x, what is that equal to? Well, it's defined to be g of h of x, all right? Let's see what this turns out to be, all right? So this is equal to, now, now h of x is the same thing as x over 2 minus x, right? That's what h of x is equal to. So, like before, we're going to have to take this expression here, x over 2 minus x, plug it into function g. Now, keep in mind, now function g has two input variables, right here and right here. You got to replace each one of these with this expression, all right? So let's do it now. I need some board space. I'm feeling I'm going to need a lot of board space here. All right, so then this is equal to, let's do it. Now I have to peek at what g is again. I'm going to scroll this down. Okay, 2x over x plus 1. 2x over x plus 1. All right, forgive me for going up and down like that. Okay, so here it is. 2 times x over 2 minus x over x over 2 minus x minus 1. Wow, that seems like a lot of work there, okay, that we're going to have to figure out, okay? So let's do that. Now, correct me if I'm wrong, but I believe this denominator here, should that be a plus 1 right there? Here, let me confirm. Let me go back up here. Yeah, it should be, see this right here? See that plus 1? So right here, ladies and gentlemen, should be a plus 1. Can we change that really quickly? Make sure that you have that correctly in your notes. So that should be a plus 1. All right, cool. I'm glad we caught that. Now, we have to work on simplifying, okay? So let's go for this. Let's do it. So then this is equal to, Now, you're going to want to distribute this 2. Now, just distribute the 2 to the x like that. So then this is equal to 2x over 2 minus x. Like that. Oh, that was a little sloppy. Here, let me go back a little bit. Minus x like that. And then over... now here, what I would suggest you to do for this denominator here, in order to for you to combine these two to be one rational expression, these two fractions to be one fraction, the number 1 must be rewritten as a fraction whose denominator is common to this one. That is, rewrite the number 1 as a fraction whose denominator is 2 minus x. So something like this, folks. X over 2 minus x plus, now here I go, I'm going to write the number 1 as a fraction whose denominator is 2 minus x. So then it would have to be 2 minus x over 2 minus x. This here is the same thing as 1, right? Okay, I'm going to have to scroll down here. All right. So equals, let's go. So the numerator, we have the numerator as 2x over 2 minus x. And then the denominator, we're able to add these two fractions together now to be one fraction. Now keep in mind, when you do this, you're going to have x plus 2 minus x. All right? So then you're going to have something like x plus 2 minus x over the common denominator of 2 minus x. By the way, this is called a complex fraction because it's a fraction within a fraction, right? So let's simplify further here. So the numerator is just 2x over 2 minus x. And then the denominator turns out to be, notice that these x's here cancel. This x and that x cancel. So then this denominator is simply just 2 over 2 minus x, like that. Okay? All right. I think we're almost done here, so just bear with me. Let's move this up some more here. So then this is equal to, all right? Now, I don't know if you remember how to divide by a fraction, but when you divide by a fraction, you keep the first fraction the same. So nothing changes for this one. Change this division to multiplication and multiply it by the reciprocal of this fraction. So basically flip this fraction. So then it would look something like this. The first fraction stays the same. Keep it the same. Keep it the same. And then change division to multiplication, and then flip the second fraction. So it'll be 2 minus x over 2. Keep the first fraction the same, change division to multiplication, flip the second fraction. Well, some people know that rule as KCF. Not KFC, like chicken, but KCF. Keep, change, flip. Keep the first fraction the same. Change division to multiplication, flip the second fraction. You use KCF whenever you are dividing a fraction by another fraction. All right, so you can see 2 minus x divides out with 2 minus x. And not only that, but 2 divides out with 2. And so this whole thing turns out to be just x. Wow. Wow. All right, very good. Now, now all of that worked out to just be x. Can we now determine that the two functions that were given to us, I keep messing this up, that the two functions that were given to us are inverses? Can we now confirm that g, I'm scrolling up here, can we confirm that g and x are inverses? This is what we just finished showing. No, not yet, because we also have to show the other direction. We also have to show that h composed with g at x is also x. So here we go, folks. We got to show the other direction. Are you with me? Let's stick with me here, and let's show the other direction for this function, all right? All right, here we go. I believe what we want to show this time around is show that h composed with g at x is also x. Hopefully that turns out to be the case. H composed with g at x means h of g of x. All right? Okay, guys, so this is equal to, now h of x is x over 2 minus x. Now, so we have something like this. So h of, and g of x is defined to be 2x over x plus 1, right? That's how we defined function g in the very beginning. All right, very good. So then this is equal to, now we're going to have to take this expression right here, this whole rational expression, and plug it into function h as your input, all right? So when you do this, you should have something like this. So 2x over x plus 1 is just the numerator over 2 minus 2x over x plus 1, like that. All right? That was me plugging this expression into function h wherever I saw the input variable. All right, very good. Whew, let's do this, guys. Now, what I would like to draw your attention on is keeping this numerator the same, all right? And maybe combining these two. But in order for these two to combine, the number 2 has to be rewritten as a fraction whose denominator is x plus 1. Rewrite the number 2 whose denominator as a fraction whose denominator is x plus 1. So maybe something like this. Let me move this over here. Yeah, that's good. So the numerator is staying the same, 2x over x plus 1. All right, but this denominator here, the number 2 must be written as a fraction whose denominator is x plus 1. So basically, I just rewrote the number 2 as a fraction whose denominator is x plus 1. All of this right here is the number 2. Here, look at x plus 1 divides out with x plus 1. And if you divide out these common factors, you're just left with 2. So this is definitely just equal to the number 2. But now you can combine these two because they have the same denominator. All right? I feel like I'm scrolling up on the screen every single time. I need more and more room here. All right, so then this is equal to, the numerator is staying the same. It's 2x over x plus 1. But now this denominator can be rewritten now. And this is what I would, let's kind of kill two birds with one stone here. Let's distribute this 2, if you don't mind, like that. All right. So then you would have 2x plus 2. And then the other numerator right here is minus 2x. And now all of this is over the common denominator of x plus 1. Cool? Let me scroll up here. And so now this is equal to, let's simplify. So then you have 2x over x plus 1. That's just the numerator alone. Over, you can see here that 2x and negative 2x cancel. Those are gone. And so then all you're left with down there is 2 over x plus 1. And then you can KCF here like we did earlier. Keep, change, flip. Okay, keep, change, flip. So then you're going to have, let's see, keep the first fraction the same. Change to multiplication and flip the second fraction, which is the reciprocal. All right, and you can see now that x plus 1 divides out with x plus 1, 2 divides out with 2, and bingo, all you're left with here is x. Whew, time to celebrate, right? So we did it. We showed both directions. We showed that G composed with H at X is equal to X, and H composed with G at X is equal to X. If you allow me to scroll up here a whole lot, I can just kind of show you everything that we did here. There it is. These two things we showed. We just finished showing that G composed with H at X is X, and H composed with G at X is equal to X. Both of these things have been satisfied, so we can confirm that G and H are indeed inverses of each other. All right? So let's actually write that down. So G and H are inverses. They're inverses of each other. All right? Whew, good job, you guys. All right, everybody, let's continue studying inverse functions. Now, the instructions say find f inverse for the given function. All right, let me give you the function that we're going to be considering. The given function is f of x is equal to 5x minus 2. All right, everybody, what we need to do is find the inverse of this function. Find the inverse of this function. Now, I don't want us to take it for granted that this function f has an inverse. Remember, we talked earlier about how not every function has an inverse function. Only functions that are one-to-one has an inverse function. So before we go try to find the inverse function of f, let's confirm. I think it would be wise of us to confirm first that f is one-to-one, because if f is not one-to-one, then its inverse does not exist. And it would be a waste of time for us to try to find it. So we want to say this. First, f is one-to-one. How do we know that? Because f is what kind of function? Because f is linear. Remember that? It's a linear function. Now, every linear function is a one-to-one function except one type of linear function, which is the constant function. Now, the constant function is a horizontal line when graphed. Horizontal lines have slope equal to 0. This function has a slope 5. In other words, it's a diagonal line. It's not horizontal. So we're safe here. We're safe to say f is a one-to-one function because f is linear, whose slope is not 0. So I'm just going to put with the slope m not 0. Remember, if the slope were 0, then it would be a horizontal line, and that's not one-to-one, which does not have an inverse function. All right, so we do know that f inverse exists, okay? So f inverse exists. We can go find it. F inverse exists, all right? We know it exists, so we can find it. Now, let us find it. All right, here we go. Let me scroll down a little bit. Since we know f inverse exists, let's find it. This is where our starting point, all right? 5x minus 2 is our function. Now, the first thing I'm going to have you do, all right, is replace f of x, that function notation, with y. Remember when we were talking about function notation, we said that f of x is representative of y. They're interchangeable. This notation, f of x, is the same thing as y. Now, the next thing I would like you to do is to swap x and y. A fancy word for swap is interchange them. Why are we interchanging x and y? Why do we have them swap places? Well, because we're trying to find f inverse. Remember, when we say inverse, we think opposite. Also, remember that instead of x going to y, y is going to go to x for f inverse. Also, remember the diagrams that I drew for you earlier on in the earlier lesson, where we reverse the correspondence. So instead of a domain value going to a range value, we reverse the correspondence because we're studying inverse functions. So because of that, we're swapping places with x and y. Okay. So now what I would ask you to do is to solve for y. Solving for y, the first thing I would do to both sides is add 2. When we say solve for y, we mean isolate y, right? So get y by itself. So now you have x plus 2 over here on the left is equal to 5y. The next thing you would do to isolate y, or solve for y, is to divide by 5. Okay, so divide both sides by 5. All right, cool. So now what we'll see, well, let me scroll up just a little bit. Your y variable is isolated on the right, and on the left you have x plus 2 all over 5. All right, let me just advise you that when you're done, what is it that you and I were finding? We were finding the inverse function of f. So before you box your answer, you want to replace y with function notation. Okay, so you just found f inverse of x, all right, which is x plus 2 over 5. You know what, just, I'm not used to reading right to left, so let's write our final answer just left to right. So f inverse of x is equal to, this is our final answer, x plus 2 all over 5. This is the inverse of f. Cool? All right. Awesome. I want you to notice something about our two functions. So let me write the original function right beneath it, all right, right beneath our final answer. Okay, so our original function was this. F of x is equal to 5x minus 2. Now pay close attention. Watch this. This is really, really, really cool. Now look at f, would you? Notice what it does to your input first. The first thing that f does to your input, which of course is x right here, the first thing that happens to x is it gets multiplied by 5, right? It gets multiplied by 5. The second thing that f does to your input after it multiplies by 5 is it subtracts it by 2. Subtraction by 2. Now, can you please look at f inverse that you and I found up here? What does f inverse do to your input and in the order that it performs it? F inverse, the first thing that it does to your input is it adds and increases it by 2 units. So the first thing it does is it adds 2 to your input. The second thing that f inverse does is it divides by 5. Divides by 5. Can you please look at these operations between f and f inverse and notice the relationship? Please notice the something really cool that's happening. Function f, the first thing it does is multiply by 5. Then it subtracts by 2. F inverse will add by 2 and then divide by 2. Do you see opposite operations? Look at f is multiplying by 5. F inverse is dividing by 5. While f is subtracting by 2, f inverse is adding by 2. So the operations between f and f inverse are opposite. The operations are opposite. Subtract 2, add 2. Multiply by 5, divide by 5. Not only are the operations opposite, but they're in the reverse order. So if f will multiply by 5 first, f inverse will do the opposite last, divide by 5. If f will subtract by 2 last, that means the first thing that f inverse will do will be to add by 2. So it's the operations are opposite and in the reverse order. So that statement here, the operations of f inverse are opposites and in the reverse order, I think would be really great for you to add to your notes. All right, so actually, before we actually go to the next example, let me see if that really made sense for you all right? So let me say a brand new example. Let me give you, I'm just trying to make something up really quickly. How about f of x is equal to 2x plus 3, 2x plus 3. Can you pause the video and can you figure out what f inverse will be knowing that the operations of f and f inverse will be opposite operations, but also in the reverse order. Can you see if you can figure that out? I'll give you some time to do that. All right, so I'm going to build this, and let's see if you and I are on the same page. I notice that what f does first is multiply by 2, and then it adds 3 last. The last thing that f does is add by 3. Therefore, the first thing that f inverse will do will be the opposite of adding 3, which is subtracting 3. Did you get that? I'll say that again. Since the last thing that f does is add 3, the first thing that f inverse will do will be subtract 3. Now, the first thing that f does is multiply by 2. That's the first thing that f does. Therefore, the last thing that f inverse will do is divide by 2. So actually, this is the inverse function of f. And we didn't have to really go through all the work and all that I showed earlier, as long as we understand that a function and its inverse will have opposite operations in the reverse order. Now, things do get a little more complicated, like in the next couple examples I show you, and so you're going to want to show all your work for the next 2 examples. All right, all right, guys, I have a brand new function for you. The instructions are the same as the previous example. Find f inverse. Let me fix that notation there. F inverse should not be written that way. Just give me a second. All right, I fixed it. Okay, find f inverse for the given function. All right, here is your brand new function. It will be f of x is equal to negative 1/2 x and then plus 3. All right, cool. Now, let's find f inverse. Now, before we go and find it, I want to make sure that you understand why f inverse even exists, all right? All right, so we do understand that f inverse does exist. It exists because f, this given function, is a linear function whose slope is non-zero or not 0. Remember, from an earlier example, we said that all linear functions are one-to-one, right? All linear functions are one-to-one as long as it's not the constant function. That is to say, as long as the slope is not 0. So because we can clearly see that the slope is negative 1/2, which is not 0, we do know that this function f is one-to-one. And if it's one-to-one, then that means f inverse exists. All right, so we do know it exists. Let's go and find it. Now, for your notes purposes, I'm going to do you the favor of giving you the steps that we followed earlier in order to find f inverse. All right, here you guys go. These are the steps. You may want to copy them down. The steps to follow in order to find the inverse of a function. All right, so follow those steps. You may want to add those to your notes now. All right, so here we go. You're going to see me apply these steps for the given function. Here we go. So step number 1, I want to replace f of x with y. Okay, very good. The next thing I want to do is interchange or swap x and y. Remember, the reason why we're doing that is because we're finding an inverse function. Remember the word opposite. Solve for y. In order to solve for y, maybe the first thing you'd want to do is subtract 3 from both sides. Okay. That will give you x minus 3 is equal to negative 1/2 y. Cool. Now the last thing is, or actually we're not done solving for y, excuse me. So maybe what you want to do to both sides at this point is multiply both sides by negative 2. Okay, so multiply this side by negative 2 and multiply this side by negative 2. Okay, the reason why negative 2 is because, first of all, a negative times a negative will be a positive, and then the 2 times 1/2, half of 2 is just 1, so y will be by itself or isolated on the right here. And then maybe over here on the left, you want to distribute the -2, all right? So then y will be equal to -2x plus 6. All right, cool. I'm ready to write down my final answer, and I'll use function notation for this, f inverse, right? And I'm also going to write it from left to right. So in other words, y, I'll write that down first, but using function notation, f inverse of x is what we found, is equal to -2x plus 6. This is the inverse of f. We found it. All right, guys, here's example 5, and we want to find the inverse function, h inverse, for the given function. All right, here is your given function. H of x is equal to 3x minus 4 over 2x plus 1. Now, if you can please take my word for it that this function is a one-to-one function. It's a rational function. You can graph it if you'd like. You can graph it using our techniques from an earlier chapter and graph the rational function and then use the horizontal line test to confirm that this rational function is one-to-one. Or you can take my word for it that it is, all right? So that we can quickly find h inverse. All right, here we go. The first thing we'll do is replace h of x with y. The next thing we'll do is interchange or swap x and y. Very good. And then we have to solve for y. All right, now, in order to solve for y, what I recommend you to do at this point is to multiply both sides by the denominator on the right. Namely, multiply both sides by 2y plus 1. I could show you why in just a second. All right, the reason why you would multiply both sides by 2y plus 1 is because this factor would be divided up with this factor, and you would have no more fraction, all right? So what you'll be left with here, of course over here, distribute the x, please, like that. And so what you'll be left with on the left is 2xy plus x is equal to 3y minus 4. Good. All right, remember what you are doing. You want to isolate y. If you want to get y by itself, then maybe what you would want to do is collect all of your y terms on one side of the equation. Okay, so let's say we're going to collect all of our y terms, maybe, I don't know, on the right. Okay, so if you're going to collect your y terms on the right, that means this term must be moved over to the right. Subtract it from both sides, okay? So this whole term is gone. On the left, you just have x is equal to 3y minus 2xy minus 4, right? None of these three terms are like terms, so you cannot combine any of them. So we just copy them down. All right, remember, again, what you're trying to do is isolate y, so at least you have all your y's on the same side. You may want to add 4 to both sides to get that over to the other side. Okay? So now what you have on the left is x plus 4 is equal to 3y minus 2xy. So what we've achieved so far, as I move this up, what we have achieved so far is that all of your y terms are on the same side of the equation. Okay, that's good. Now, if you want to isolate y, the next thing you may consider doing is factoring the common factor of y out of this right-hand side expression. That would leave you with 3 minus 2x, like that. Okay? And now, maybe what you would want to do is to divide both sides by 3 minus 2x. 3 minus 2x. Divide both sides. After all, division is the opposite of multiplication. And right now, y is being multiplied by 3 minus 2x. So then we should divide both sides by 3 minus 2x, which would get rid of that whole factor there, you know? So 3 minus 2x. All right, so y is isolated on the right. And on the left, you have x plus 4 over 3 minus 2x. Now, I'm going to switch this around and put y on the left side of the equation. Hold on just a second. So you're going to have y is equal to x plus 4 over 3 minus 2x. The last step in this process is to replace y with function notation. Remember, your original function was named h, wasn't it? So we found h inverse is what we just finished finding. H inverse of x is equal to x plus 4 over 3 minus 2x. So this is the inverse function of h. Wow, good job, you guys. All right, you guys, we've reached the last example of this section. Determine if each function is one-to-one. If it is, find its inverse. Remember that if a function is not one-to-one, then that means it does not have an inverse. All right, here is the first function I want you to consider. P of x is equal to x squared minus 4x plus 3. Now, is this function one-to-one? Well, because you and I already studied quadratic functions, you and I should know very quickly that this would be a parabola. The graph would be a parabola opening upward, right? Would this pass the horizontal line test? No, it would fail the horizontal line test because the horizontal line would cross your parabola twice, correct? So because this function, when graphed, would fail the horizontal line test, HLT just represents horizontal line test, the function P is not one-to-one. If it is not one-to-one, then that means its inverse does not exist. So P inverse of x, this inverse function, does not exist. So of course we're not gonna, I'm writing really sloppily here, sorry, but we're not gonna go try to find something that does not exist. So this problem is done. All right, cool. Let me give you a different function now, all right? So this function is done, all right? Now please consider q of x is equal to the square root of x plus 1 minus 5. Now, this function, ladies and gentlemen, is one-to-one. Now, you can confirm that because if you were to graph it. If you were to graph it, then this graph, we know this by its parent graph, or the parent function, would look something like this. Like that, okay? The function would look like this. And no matter where you choose to draw the horizontal line, it will cross your function only one time, right there. So it passes the horizontal line test, which means it is one-to-one. All right, cool. Because it passes the horizontal line test, and of course you can graph this function really quickly in Desmos.com, or you can use the techniques that we studied earlier in this class with function transformations to graph this function. Nevertheless, when you do graph the function, you'll find that it does pass the horizontal line test, which means it is one-to-one. Because it's one-to-one, its inverse exists. Let me write that down. So Q inverse of x exists. All right? Because it exists, we should go find it. All right, let's do that now. Let's go find it. The first thing that we want to do is replace q of x with y, right? So look at this right here. Replace q of x with y. The next thing we want to do is interchange x and y. Remember these steps from earlier. And then solve for y. Okay, all right, let's solve for y. Let me move this up a bit here. When we solve for y, the next thing you may want to consider doing is adding 5 to both sides. After adding 5 to both sides, then you have x plus 5 is equal to the square root of y plus 1. To continue solving for y, or isolating y, the next thing you might want to do is get rid of that square root. Do you know what you would do to both sides to get rid of that square root? If you said square both sides, or thought to yourself, we should square both sides, and that is correct. Good job. If you square both sides, notice that on the left you would have x plus 5 quantity squared, which we know is x plus 5 times x plus 5. While on the right, it's just y plus 1. Okay? The left-hand side, of course, you would have to distribute. Some of you know this as FOIL. Like that. All right, so then the left-hand side would be x squared plus 5x plus another 5x plus 25 is equal to y plus 1. What we can do in this step is, well, we can do two things. We can subtract 1 from both sides. After all, we are trying to isolate y. And we can also add these two like terms here to give you x squared plus 10x plus 24 is equal to y. All right, very good. So you did it. Just for notation purposes, remember that we were finding the inverse of q of x. So then we want to replace y with q inverse of x, which is x squared plus 10x plus 24. Okay? This is the inverse function of q. Good job. Now, the next thing I'm going to have you do is find the domain and range for q inverse of x. This is really important, all right? So let me kind of recap what we found so far, all right? So allow me to recap just for a second to wrap up this lesson, okay? Q of x is equal to the square root of x plus 1 minus 5. That's q of x. All right, so that was our starting point. Can you help me figure out what the domain would be of this function? The domain. Let me actually write that out. The domain. Now, you see the square root. You see the square root. So we talked earlier of how x plus 1, the radicand, must be greater than or equal to 0, correct? So when you actually solve for x here, by subtracting 1 from both sides, you find that x has to be greater than or equal to negative 1. So then the domain for q of x in interval notation would be from negative 1 to positive infinity, right? This is the domain for q of x. To wrap this up, what about the range for q of x? Well, if you were to graph this function, either by using function transformations or by just, using a graphing calculator like Desmos.com, you would find that the lowest y value or the lowest function value is negative 5. So the range here, and you can confirm this on your own if you'd like, the range would be from negative 5 to positive infinity. Now, these two things are really important, the domain and range. Now, these are the domain and the range for q of x, all right? The domain and range for q of x. Now, in the early part of this lesson, we talked about how the domain becomes your range and the range becomes your domain when you're studying inverse functions. So with that being said, Q inverse of x, which we found to be x squared plus 10x plus 24. This is what we found earlier. We now know what the domain and range will be for Q inverse of x. The domain for Q inverse of x will be the same as the range for Q of x. They swap. And the range for Q inverse of x will be the same as the domain for Q of x. All right? So let me write that down. So -1 to positive infinity. All right? So this is really, really, really important. Okay? We know the domain and range for Q inverse because we know the domain and range for Q. All right? If you know the domain and range for Q, you automatically know the domain and range for Q inverse. They just swap. All right? So I think I want to add something to your notes before we close this section out. All right, to wrap this up, maybe add this to your notes. The domain of function f becomes the range of f inverse. The range of function f becomes the domain of f inverse. So again, if you know the domain and range of a function, then you automatically should know the domain and range of its inverse function. All right, everybody, this completes section 4.2 entitled Inverse Functions.